Hello everybody, I'm Arlene Magalhães and I will present the work Indexed Log File toward Main-Member Database Instant Recovery. Main-Member databases can provide very high throughput, given that the primary database resides in main memory. However, these systems are more sensitive to system failures because of memory volatility. Most of main memory databases store a logical redo on log in which records are written sequentially to secondary memory. As the log file is sequential, after a failure, the log records are sequentially read to recover the database. It's important to point out that the database is available only after the recovery process is finished. In this sense, we propose an instant recovery approach for main-memory databases. The approach allows the system to schedule even during recovery process, giving the impression that the system was instantly restored. The main idea is to organize the log file as an index structure. Thus, the technique indexes the log records in a B plus tree using tuple ID as search key in background. It's important to note that the tree loses the global LSN order, but the tree still maintains the local LSN order on each node to restore a single tuple. A single search on the B plus tree, which is in this case represents the log file, can retrieve all the log records needed to redo a tuple. Thus, after a failure, the system recovers the database incrementally by traversing the B plus tree. Besides, if a transaction needs tuples that have not yet been loaded into memory, the system is able to restore them on demand. This mechanism, therefore, provide high availability since transactions can access tuples as soon as they are restored. This slide illustrates an abstract model of the architecture to implement the proposed instant recovery approach. First, we will see the logging technique. During transaction processing, log records are sequentially flushed to the log file by the logger component. The indexer component monitors the entries in the sequential log and indexes the records. This indexing process is asynchronous to transaction commit operation. Thus, the transactions do not wait for the indexing process. It's important to highlight that only the indexed log is used to recover the database. However, the sequential log is maintained because in the case of index corruption, the system can rebuild the indexed log. In this case, the rebuilding process may delay the recovery start. Now, let's show the recovery process. After, after a system failure, first the system checks if any records have not yet been indexed and indexes them. Then the recovery can begin and new transactions can be performed. The historic component begins redoing tuples into memory. After a tuple is restored, it is tagged as restored and a transaction can use it. If a transaction needs a tuple T that has not been yet loaded into memory, the scheduler component requests the restore for the tuple T. After all B plus 3 nodes have been visited, the database is completed restored and the recovery process can be finished. The proposed instant recovery approach has been implemented in the in-memory database system Redis. We performed experiments in the three different scenarios. In the first scenario, we have used the full recovery implemented by Redis database. In the second scenario, we have used the instant recovery approach proposed in this work. To evaluate the indexing right during transaction processing, the third scenario is an approach derived from the proposed instant recovery approach in which transactions should wait the indexing of log records, that is, a synchronous log indexing. We used Mentai benchmark to simulate workloads. Mentai is a benchmarking tool for Redis that provides options for configuring custom workloads. The first group of experiments used a heads database containing 99,000 tuples. The log files were generated using our logging approach. The sequential log had 11.8 gigabytes and 106 million records. For each scenario, the system has been shut down to simulate a system failure. Thereafter, during the database restart, a workload has been submitted. This graphic shows the transaction throughput during workload submission. The vertical dashed lines indicate the final recovery time for each scenario. The results shows that the full recovery in head was the fastest approach to recover the database. However, the instant recovery in blue could perform transactions since the system restart, and it was the fastest approach to finish the workload execution, proving that our approach provides high availability and high transaction throughput rates. In the third scenario, in yellow, the synchronous log indexing degraded system performance. Additionally, we performed experiments regarding different databases. For example, the largest database, DB4, has almost 400,000 tuples and 640 million log records. The goal was to observe the behavior and performance of the recovery approach when the database and log file increase in size. For each experiment, after simulating a failure, we measured the recovery time, the average transaction throughput rate, and the total workload execution time for each database. In the first graphic, as expected, the size of the database has impacted the recovery time. The default recovery was the fastest for all databases. This is because the random access pattern of the indexed log file. But the full recovery can perform transactions only after the full recovery. On the other hand, the instant recovery is able to perform transactions since the database restart. Besides, as shown in the ordered graphics, the full recovery and our approach have a similar average transaction throughput and workload execution time for all databases. These results show the viability of our approach due its high availability and high transaction throughput rates. Our conclusions. In this work, we have proposed an instant recovery approach that can perform transactions during recovery process incrementally and on demand by an indexed log. The results of the experiments shows that the proposed recovery approach can reduce the perceived time to repair a database. Besides, the impact of asynchronous log indexing is minimal during transaction processing. As future work, we intend to implement a first checkpoint to the indexed log to accelerate the recovery process and free up log space. The idea is to propagate log record actions for the most frequently accessed tuples. For each of those tuples, a single log record is generated in order to replace the previous log records in a leaf of the B plus tree. And finally, we also intend to do the checkpoint process during recovery for each restored tuple. Thus, the next recovery will be faster if successive failures occur. So that's all. Thank you.